Welcome to the group exhibit Hydrogen, Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Bouakas. Please have a seat, join us for some coffee and some refreshments. I would also like to welcome our online guests watching the live streaming. The upcoming presentation will be regarding multi-fuel processing for PEM fuel cell stacks. Please welcome with me on stage the Technical Director of NOVOROCS Technologies, Dr. Phillip Hutton. Thank you.
Thank you. So my name is Dr. Phillip Hutton. I'm the Technical Director for NOVOROCS Technologies. NOVOROCS Technologies is a US-based company located in Rochester, New York. Just to give you an overview of our history, we are a joint venture between a solid oxide fuel cell company and a catalyst company. Our core expertise is in catalyst design and fabrication, reactor design and fabrication, and testing and commercialization. This slide shows you some images of some products we've made for customers in the recent past. In the far left there is a NO tail gas afterburner. We actually have that at our booth at D37, so if you want to see it in person, please visit our booth after the presentation. The middle top image is of a reformer test bench we built for NASA to help test some of our metal foam catalysts for their SOFC program. On the upper right is a pilot scale, skid-mounted pilot scale steam methane reformer. It converts natural gas to syngas for a hydrogen production system for a fuel cell company. What we're really excited about right now are our new line of metal foam catalysts. We deposit catalysts on metal foam substrates. We feel that the metal foam provides enhanced thermal characteristics and enhanced flow characteristics and mixing. And of course we do catalytic combustors in which we make platinum-based catalytic combustors that convert fuel to heat without a flame. Why do we want to introduce fuel processing to PEM stacks? PEM stacks are a very mature technology. It converts hydrogen to power at very high efficiencies. So why complicate the matter? The reason we want to complicate the matter is because in its current configuration, the hydrogen gas is introduced to the PEM stack in a dead-ended configuration, which means that the hydrogen gas stops at the PEM, which means that any impurities in the hydrogen gas end up poisoning the PEM cell, building up and poisoning the PEM cell. What we feel, and what that requires, that means that your hydrogen has to be extremely pure, 99.99% to 99.999% pure, for it to be a viable fuel for your PEM fuel cell stack. We feel that there's an alternative way to run that PEM stack, and that's by running it in an open configuration. When we say open configuration, we mean that you run the fuel past the anode. About 80% of the hydrogen is used in the PEM fuel cell stack. The 20% that exits the anode is then run through a combustor, a catalytic combustor, and that heat can be used to either for space heating, or it can be used for your reformer on the front end. This is a block diagram of a typical fuel processing system, multi-fuel processing system for a fuel cell. And your first step is to take either natural gas, methanol, gasoline, dimethyl ether, DMM, or ethanol. Run that through either a partial oxidation reformer or steam methane or a steam reformer. And what you get coming out of the reformer is a syngas. It's a hydrogen-rich syngas. Depending on the fuel and the operating conditions, your syngas will have between 1 to 10% carbon monoxide. Carbon monoxide is the gas we're concerned about. More specifically, carbon monoxide is the gas we want to minimize as much as possible for the lower temperature fuel cells. this syngas is directly usable in a solid oxide fuel cell or a molten carbon fuel cell with no additional processing or major processing involved. If you want to use this syngas in either a phosphoric acid fuel cell or a high temperature PEM cell, you have to reduce that carbon monoxide from about 10% down to about 1%. And you can do this relatively straightforwardly in a water gas shift reactor at a temperature range of 250 to 500. If you want to use it in a low temperature PEM, which is arguably the most developed fuel cell we currently have, you would have to run it through an additional methanation reactor, either a methanation reactor or a partial CO oxidation reactor. And what this does is this either converts that CO to carbon dioxide or methane. And both the carbon dioxide and methane are treated as inerts in the actual PEM fuel cell. And this last step will get your carbon monoxide down to around 10 to 20 ppm, which is about where you want to be if you're running it through a PEM fuel cell. So this shows you an experimental diagram of an experiment Dr. Snitnikoff did recently. And what he did was run methanol, DME, dimethyl ether, formic acid, and DMM through a steam reformer at 250 to 300. And the reason he used those fuels were because they have similar reforming characteristics. Their temperature range is very similar in about 300, 350. The syngas that comes out of it at this temperature range has less than 1% volume carbon monoxide. Since it has less than 1% volume carbon monoxide, that syngas can be cooled and used directly in a fuel cell. Used directly in a phosphoric acid fuel cell or high temperature PEM fuel cell. We used it in a high temperature PEM fuel cell. If you wanted to use that syngas in a low temperature PEM fuel cell, you would have to run it through an additional methanation reactor. We like methanation as opposed to partial oxidation of CO because with methanation we don't have to introduce any additional reactants. We could put the reactor in line with the syngas, and it's in the same temperature range as that the syngas is already at. The output will have approximately 10 ppm CO, and we can run that right into the PEM fuel cell. This gives you some fuel and catalyst characteristics. For methanol, DMM, DME, we get about 20 or 0.2 grams of hydrogen per gram of fuel, and our costs for those fuels are around $400 to $2,000 per ton. To give you an idea, I think gasoline in the U.S., order of magnitude around $1,000 per ton for gasoline. So the cost of the fuel is comparable. Formic acid, the results are a little different. We only get 0.04 grams of hydrogen per gram of fuel, and the cost is very reasonable at $500 per ton for formic acid. The kind of catalyst we use for our steam reformer was a copper-based catalyst. You can use copper on aluminum oxide, copper zinc oxide on aluminum oxide, copper oxide, cerium oxide on aluminum oxide. We use the copper zinc. And this shows the laboratory results. And what's important for this is that for both DME, methanol, and DMM, at temperatures of around 300 to 350 C, our gas composition was equilibrium. So we had equilibrium conversions. For formic acid, our temperature, we ran that at much lower temperatures, between 175 to 250, but we could run that at 300. Gives you a summary of initial results. What you see for most of the fuels, we had about 60% hydrogen in the syngas and less than 1% CO. Our productivity was very high, 15 liters of gas per hour per gram of catalyst. That means that we didn't have to use much catalyst to get that done. This gives you an image of the steam reformer and the PEM fuel cell stack. We ran this for about 100 to 200 hours. 300 watts, produce 220 volts AC. And this shows you the components of the actual system. What if we're going again, what if we wanted to run it into a low temperature PEM, and this is a high temperature PEM. But if we wanted to run into a low temperature PEM, we'd have to run it through a CO preferential methanation reactor. This is a simple design. We would take the methane after it goes through the PEM fuel cell stack. We'd combust that in a tail gas combustor and then use that heat for either space heating or to support the reformer at the front end. This is a separate project that Dr. Snitnikoff did, in which he put the water gas shift reactor, the methane reactor, in one unit. And you can see that because they're operating at the same temperature range, it's a simple design. You run it, the only thing you're changing is the catalyst. And this shows the output. And what you see here is that your CO is down around 10 to 20 parts per million. So this shows the experimental outputs of that methanation reactor you saw earlier. So what do we want to do, and why am I here? Okay, we want to translate those lab results into a turnkey product. Now, our core competency is in reforming and catalyst design. We are looking for stack designers, system designers with stacks, to work with us and partner with us to develop a turnkey product that we can then market. If you are interested, please visit us at booth number 37 and talk to us. We would love to walk away from Hanover in a couple of days with a partner to move forward on developing a turnkey system. Thank you.
Thank you very much. Thank you, Philip. Please stay with me on stage just a more second. Are there any questions to NOVOROCS? Maybe you want to discuss this in private if you want to partner up with him. Yeah, visit their booth D37. Thank you one more time.
Thank you. Thank you.
So the next presentation will continue at 11 a.m. I'm very much looking forward. It will be by ITM regarding the Big Hit project. I'm really curious what you're going to talk about us, what you're going to tell us. Please stay with us, have a coffee, have some refreshments. There are two lovely ladies available, and see you in a few minutes. Thank you very much.